The Nernst equation, like any physics or chemistry equation, can be done as a quick sketch in which the various parts of the equation are partly sketched so that it helps you understand what's going on in the equation. It's called Nernst equation after Nernst. It really should be called the equilibrium potential equation because what it does is gives you the value for the equilibrium potential or charge for a particular concentration difference of an ion in an equation. The Nernst equation is in the form of the equilibrium potential for some ion equals RT over ZF times the natural log of concentration outside of the cell over the concentration inside. So what are these? R is the gas constant. T is temperature in degrees Kelvin. Z is the valence of the ion, +1, -1, +2, and so on. And F is the Faraday constant. But what are these? What do these all represent? So let's look at a cell that might be in an equilibrium with about 1 potassium outside for about 10 potassium ions inside. And the question is, what's going to put that in equilibrium if there are channels open for the potassium to get in or out? Simply considering concentration, there are 10 times more potassiums inside, so there are 10 times more opportunities per unit of time for potassium to hit that channel and go out than there are for the 1/10 as many potassiums to come in. So without charge playing a role, what we'd expect over time is for half of these to leave and we'd wind up with the same concentration inside and outside. But if we added negative charge here, then that negative charge could hold potassiums inside. To make it seem really simple, let's just do 1 negative charge for each of these. And if all of them except for this one has a negative charge holding it in place, then this is the only one free to bounce around on the inside, and this is the only one bouncing around on the outside. And now we have a point where, in this hypothetical and simplified example, what we've got is 9 out of 10 of these are not free to move. They're held in place by a negative charge. Only one is free to move, and that gives us an equilibrium where we're just as likely to have one come in as one go out. But what is that charge? So the question is, what is that equilibrium potential? It's the charge minus whatever, minus 70, minus 100, minus 40. It's the charge that is going to hold 10 times as many potassiums inside as outside. By the way, I've simplified this a bit. Typically, a cell has about 20 times more potassium inside than outside, but I didn't want to draw 20 potassium ions. Okay, so let's break this down and start talking about what these things are. R is the gas constant, and it is the amount of random molecular movement per degree Kelvin. So we can think of it if we had a diagram like this where we had 0, 1, 2, 3, 4 degrees Kelvin, and then some amount of just the total of all the random molecular motion. Then at 0, of course, nothing is moving. That's the whole point of absolute 0. So at absolute 0 degrees Kelvin, nothing's moving. The gas constant tells us that there's going to be this much more at 1 degree. So there's that much more movement at 1 degree, and at every degree change, it's exactly the same increase. So if we want to know the total molecular movement at a particular temperature, it's going to be the gas constant, this, times the number of degrees. So R times T can be thought of as where each one of these represents the amount of molecular motion in 1 degree, but we're multiplying it by the temperature to get the total. So RT at the top here is telling us how much random molecular motion is there. In other words, how much random molecular motion. The more molecular motion, the more times these things are going to hit these openings. And as you might guess, the more these things are moving, the more easily a potassium could escape a nearby negative charge. It's moving fast, more able to escape and move out. So the more random molecular motion, the higher temperature, the more negative charge it's going to take to hold that in. Okay, so what about the valence and the Faraday constant? Well, the Faraday constant is a measure of the attraction of opposite charges, or you could equally think of it as the repulsion of same charges. So the Faraday constant tells us what is the force that's pushing same charges apart or opposite charges being held together. And you, of course, have to multiply it by the valence, because a +1 will have half the charge, half the effect of a +2. So ZF is telling us how tightly negative charge is going to hold these ions in place. The way I've drawn it here, I've simplified by saying, okay, let's assume all of these have a negative charge nearby. They're held in place. This one's free to move. This one's free to move. Total up the negative charge here, and that would be the equilibrium potential. But of course, we've also got this other term, concentration outside versus inside, and we can simply represent that by K plus over K plus, K plus, K plus, until we get to 10. But of course, the K pluses drop out. What we're going to wind up with is 1/10. 1/10, we're taking the natural log of 1/10 here. Natural log of a fraction is negative, and so that means our equilibrium potential is going to be negative in the case of potassium being held inside. That makes sense because it's going to take a negative charge to hold this in. How much negative charge? For this concentration, this particular concentration, in this case I've made a 10-fold concentration gradient. At this particular temperature, in other words, this amount of random molecular motion, but this is tending to make those ions move. This one is holding them in place, the negative charge in here. This is the force of negative charge holding them in. So it should make sense that for particular concentration difference, the total amount of movement divided by the effective charge to, in this case, hold potassium in, should tell us what the equilibrium is. And the equilibrium is going to be the amount of charge that gives you no net movement. And I hope it makes sense to you now that you need to have the concentration gradient in the equation, because that's what tells you what's the proportional difference. How the higher the concentration, obviously you're going to need more negative charge in here. Random molecular motion matters. If we go to the simplest case, let's say absolute 0, then this term becomes 0. There's no movement. And when that term becomes 0, you don't need any charge to maintain that concentration gradient. And so the equilibrium is 0. So it should make sense to you that as molecules are moving slower and slower, the equilibrium potential gets closer and closer to 0. You need less and less negative charge to hold those potassiums in place. On the other hand, the hotter it gets, the more these are moving. You can think of that as an ability of, even though these this positive and negative charge are strongly attracted to each other, you can think of it as the ease with which potassium escapes that negative charge and becomes free to move out. In a universe where the Faraday constant was different, then that would change the amount of charge. If the Faraday constant was larger, you wouldn't need as much charge to hold this much potassium in. If the Faraday constant is lower, in other words, less attraction, then you would need more charge. So I hope this makes sense as a quick sketched equation. If you were going to do it as an equation, then it would be equilibrium for whatever ion, in this case it's K plus, equals the total molecular movement divided by the valence, and I'll just leave that, we'll just leave that as a Z times the attraction of positive to minus, as I've discussed it in this case, times natural log of concentration out over concentration in. And the Goldman equation is the extension of the Nernst equation to figure out what an actual membrane potential is by considering all the ions that have a high enough concentration to make a difference and that are able to move across the membrane. But it is in some ways just an expansion. Well, it is just an expansion of the Nernst equation with the structure changed a little bit so that you can consider each ion independently and combine all their effects.